Hello and welcome. So let me first start with a reminder of this week's material. So we are in chapter 24 and we are talking about capacitance. And we introduced capacitance on Monday. Today we are going to talk about dielectrics and electric energy storage. Again, these are your reading assignments and these are suggested problems. So here's what we did on Monday. On Monday, we introduced these parallel plates, which we worked previously to find the electric field. And we called them capacitors. And we said they could be used for things like energy storage in circuits. And the amount of charge on a capacitor was proportional to the amount of voltage it was under. So there was like a relation like this. Q was equal to some proportionality constant, which we call capacitance times voltage. So this C was a purely geometrical quantity, at least mostly. And for like a simple geometry, we obtained C is equal to epsilon naught, area of this thing times the divided by the distance between the plates. So using this formula, we calculated capacitance of capacitors in different configurations, like for example, a cylinder, a shell, two lines, and so on. So we said when capacitors are connected in parallel in a circuit, the net capacitance was equal to sum of individual capacitances. And when they were connected in series, we said you have to do this inverse summation. Basically, 1 over C equivalent was equal to 1 over C1 plus 1 over C2 plus 1 over C3. We did some exercises for that and we did some more exercises, okay? So today we are going to talk about electric energy storage. So we said capacitors are good for electric energy storage. So let's see how that works, okay? To start with, I want to start with like a capacitor. Let this be my capacitor. And I want to put certain amount of charge on it. Let's say plus Q here and minus Q. And I want to remind you the capacitance was defined by total charge divided by voltage. So this thing should also have like a certain voltage. Let's call this V. Okay. Now I would like to calculate the work needed to increase the charge by like a little bit amount, okay? I want to calculate the work I need to do to take a little bit of charge from here with dq and move it here, okay? Or if you like, I want to find the work, I need to increase this dq by dq, okay? So I know how to do this. That is like, if I have like a certain amount of charge and if I have the potential, that's the amount of work I need to do. That's what we learned last week, right? Now I would like to use this relation. So if you invert this guy, V is equal to what? V should be equal to Q divided by C. So let me plug this back in. So this is going to be equal to dq Q over C. Now, if I integrate over all possible Q's, like basically Q is equal to, like, let's integrate this from, so this one will give me W integral, and I want to integrate this, okay, from no charge to charge. If I do this, I'm going to find the total work needed to put this capacitor in this form, which will give me something like this, 1 over 2C Q squared. But this should be the energy stored in the capacitor. That work I do must go into the stored energy in the capacitor. So I have this formula, 1 over 2, 1 over C times Q squared. Okay. So I think by using this relation, I can put what I obtained in different forms. For example, I can multiply this with Q, with C, and divide by C, and I will get something like this. Let's see, 1 over 2. If you multiply with C and divide by C, you have something like C squared. And if I use C Okay, C squared Q over C is equal to V. So it's going to be C squared. This is V squared. So I can do this thing. So this is C times V squared. Or what else can I do? I have something in terms of C and Q. I have something in terms of C and V. So I should have something in terms of Q and V. And for this, I need to just plug in C, which is Q over V times V squared. I can cancel these V. So, okay, that's good enough. Q times V. Okay, whichever you like. So I first obtained this, and I used this over and over again. I obtained this, which was equal to this or this. So this was written in terms of C and Q. This was written in terms of C and V, and this one was written in terms of Q and V. Okay. So if you have V, if you remember, we had like some V of a single charge. It had some potential, and we put a second charge. And we said, okay, the work needed to be done to take this charge to infinity was also equal to Q times V. So here's an example. A parallel plate capacitor carries a charge Q and is then disconnected from the battery. All right, this seems to be disconnected from the battery. The two plates are initially separated by a distance d, and suppose the plates are pulled apart until the separation is 2d. How has the energy stored in this capacitor changed? Okay, so basically initially U is equal to 1/2 Q squared over C. I can use this because I know once the battery is charged and disconnected, what is constant is total charge in the battery, and the capacitance will be a geometrical constant. So U initial, if you like, is equal to C initial, and C initial is equal to epsilon naught A over D, and U final, I can do the same thing, 1/2 Q squared over C final. Be careful, I use the same Q because Q cannot change. And for C, I calculate something like that. C final is equal to epsilon naught E. How much did we increase? D is increased from D to 2D. So this will be 2D. Then U final, if you plug this in, is going to be equal to 2 times U initial. So the energy stored will be twice as much for this case. So which makes sense, because if this thing is disconnected from everything and then I pull this, there's like a certain force I need to apply, and this force comes with some F dot dx, and that should be equal to increase of energy of the capacitor. That's where this increase comes from. Okay. Now I want to calculate this stored energy in terms of purely electric fields. Okay, and let's see if I can switch this thing to electric field. So the C I calculate, or energy I calculated, was something like this. U was equal to, which one should I use? Let's use 1/2 C V squared, 1/2 C V squared. Now I know C should be equal to, C is equal to epsilon naught A over D. If I have certain plates of area with some distance, that's the capacitance. And V, what is the V in between these two things? It's like a constant electric field. So I can also write an expression for V. V should be equal to some electric field times distance. So if I put these numbers together, U is equal to 1/2 epsilon naught A over D. And if I take the square of V, it's like E squared times D squared. And if I combine factors, I have something like this. A times D times E squared. And this thing here is area area times the distance, which is volume. So this thing is volume. So if I define something like energy per volume, I divide both sides with the volume, divide this with this. So you get energy density, which is the density per unit volume. So it's something like this, which is a nice quantity, right? U is equal to 1/2 epsilon naught E squared. So maybe we can do an example about energy storage and then exercise. So here's the problem. Example 10 from your book. The plates of a parallel plate capacitor have area A and separation X. I just wrote it like this, some area and X, and are connected to a battery with voltage V. While connected to the battery, the plates are pulled apart. Okay, this thing seems to be important. While connected to the battery, plates are pulled apart until they are separated by 3x. And the question, what are the initial and final energies stored in the capacitor? And B, how much work is required to pull the plates apart, assuming constant speed, and C, how much energy is exchanged with the battery. So now, since it is connected to the battery during this operation, the voltage across the capacitor, whatever it is, should be constant V, because battery will supply that voltage no matter what you do, right? So okay, let's try to write U initial, right? What are the initial and final energies stored in the capacitor? U initial is 1/2 C V squared, right? Can I use this? Let's look at the available formulas we have. So we can use this guy, but we don't know if charge is constant. We can use this guy. Now we know voltage is changing, but this will give us a good voltage constant, so this will give us a good measure. And as you pull the plates apart, only the capacitance will change. We can use this one, or we can not use this one because we don't know about the charge. So let's just copy this guy and put it here. Now let's put C, okay. C is equal to epsilon naught area divided by X. Then U initial is equal to 1/2 epsilon naught area over X times V squared. So U final is similarly 1/2 some, okay, this was initial, this is final, and voltages are the same because of the battery. And C final, this is C initial, C final is equal to epsilon naught area divided by now 3x. Then U final should be equal to 1/2 epsilon naught A over 3x V squared. So now delta U is equal to what? So U final plus U initial, this is going to be 1/2 epsilon naught A over X times V squared. So 1/3 minus 1 is equal to minus 2 over 3, right? Minus 2 over 3. So this was A. B, how much work is required to pull the plates apart? B. So how do I calculate work? I calculate the work by its definition, right? It's like F dot dx. And the force is what? Suppose I am pulling this plate like this, and the force, and to keep it going with constant velocity, I need to supply equal and opposite force coming from the other plate. So the question boils down to what is the force coming from this plate on this plate, and that's equal to simple, right? Charge on this plate times electric field coming from this plate. So let's write it. So Q on the plate times electric field. So I have to be careful because I only need to take the electric field coming from this plate. E from other plate. And I know how to do this. E is equal to sigma over 2 epsilon naught per plate, if you like, EI. And if you sum two of these, I get the net electric field in between. But that's not what I need. I only need one contribution. So, and CQ is equal to what? Q is equal to sigma times area, or sigma is equal to Q over area, whichever one you like. So let's write these things. So Q is equal to, okay, sigma times area and electric field from the other plate. Okay, and this is going to be equal to what? Sigma divided by 2 epsilon naught. And this is the force, and I need to integrate. Now, okay. Remember, let's remind us what we did. Okay, this thing is good. So remember, C was defined as Q over V, then Q should be equal to C times V. Right? I can write, okay, A here and divide it by A, and this is going to be equal to 1 over 2 epsilon naught area, and this is Q squared, but Q is equal to C times V, so this is like C squared V squared. This is dx, and now V is constant. I can take that out too. This is going to be equal to V squared over 2 epsilon naught area, and C squared is equal to what? I found an expression here. This is going to be epsilon naught area. So this is epsilon square, area square, x square, dx, and x goes from x to 3x. All right, now I can do some cancellations. This area cancel with this epsilon cancel with this. So this is going to be equal to 1/2 V squared epsilon naught area times integral 1 over x. So if I take the derivative, I get the correct integral, and it should go from x to 3x. So this is minus 1 over 3x plus 1 over x. It's 3, this is equal to 2 over 3x. So this should be equal to 1/2 V squared epsilon naught area times 2 over 3x. Okay. And C, okay, how much energy is exchanged with the battery? Okay. So I have like change in potential energy of the capacitor. I have the work I've done. The final thing is the battery, how much energy is changed with the battery. So all these three things should add up. So work I have done should be equal to change in energy of the capacitors plus change in energy of battery, or energy exchange with the battery. So energy exchange with the battery should be equal to W minus delta U capacitors, which is equal to, okay, I have 1/3. Okay, this is 1 over x. This guy is 1 over x. 1/3 epsilon naught A over x times V squared. Okay, this guy also, there's like a nice two-factor cancellation. And minus minus is plus, plus. So minus this guy is plus, because there's like an overall minus here. So this is going to be equal to 1/3 epsilon naught A over x times V squared. So total energy is equal to 2 over 3 epsilon A over x times V squared. Okay? What about part C? Can I repeat? Yes. So in the first part, I simply calculated the initial energy stored in the capacitor and the final energy stored in the capacitor. And the change should give me an energy change in the capacitor, right? In the second part, I calculated the work done on the system, or the work I have done on the system by pulling this. And during this operation, I need to remember there's always like a battery, right? Whatever you do, battery will do something else. So at the end, everything should add up. The work I have done should be equal to change in energy of the capacitor plus change in energy of the battery, right? There is nothing else I can add here. All the processes are taken into account. And I know W, and I calculated delta U capacitor, so I can solve this equation for battery, and that's what I found. So amount of energy exchange with the battery should balance this equation. Should work done be equal to energy change in the capacitor? Should work done be equal? So work done is not equal to energy change in the capacitor, right? There is also battery. So this thing is connected to battery all the time. So you have to think about what will go with battery. Battery will not just sit there and not do nothing, right? Battery will do its own thing. Whatever you do, battery will do it too. So for that, you need to do this thing. Not only, you're saying just this one, that would miss the battery, right? Now I want to introduce something called dielectrics. So far the capacitors we had, they were empty in between. And actually we can insert something in between and we can ask what happens. And what happens, actually this is like a more like an empirical question, and we can think about this in two ways. So the first way, we can think about constant voltage, V constant, like we can insert the electric while the capacitor is connected to a battery, or like we said in the previous examples, we can think about Q constant. So we can charge the battery and take it out of the circuit and insert the electric. So what is fun in both cases, let me just tell you what happens. In this case, you have a charge, right? And the voltage should always be the same. This is always the V, but battery can only change total charge here, Q and Q prime, minus Q prime, minus Q prime. And empirically, what is found is this charge increases by some constant, K times Q0, okay? And this one changes by minus K times Q0. So if you look at the capacitance, this new thing is new charge, which is K times initial charge divided by the same voltage. So you are going to find some K times C naught. So this K is something bigger than 1, as long as you have a dielectric in it. In the second case, I already charged my capacitor and I have a certain amount of charge here, Q and minus Q. I cannot change this anymore. And after I put this dielectric in, I can measure the voltage and see what happens. And empirically, what is found is voltage changes by some constant. The voltage across the capacitor drops with some constant. And if you calculate the C in this case, C is equal to, so initial Q, which didn't change, divided by V0 over K, which what you'll find is the same thing, K times C0. So the upshot is, in each case, by putting a dielectric in the capacitor, you increase the capacitance by a factor K. Okay. And here are some numbers for what you can, of course, put different things in this capacitor. For example, if you don't put anything, that K, which increases, is 1. If you let air circulate in your capacitor, it increases just a little bit. So you can almost think like air in the capacitor with vacuum for all practical purposes. So you can, for example, put paper or quartz, and you can increase your capacitor by 3 to 4 factors. You can put porcelain or some other material, you can increase by almost 10-fold. If you put like some fancy materials, you increase it by hundreds of factors. Okay. So now let's look at the formula we derived earlier. Earlier we said capacitance was some epsilon naught A over D. Now in this new case, it's going to be some kappa epsilon or K epsilon naught times A over D. And this thing, I want to give it a name. I call it this E, the epsilon without zero, and it's called material permittivity. Okay. So I can ask, okay, this is what happens to capacitance. I can ask what happens to electric field in between the plates. So, and for all of these things, I assume that the gap is completely filled. And if that's the case, so we know electric field is written in terms of voltage as some V naught divided by distance. And if voltage goes to some value divided by K, electric field, let's call this ED with the dielectric, is going to also drop with some factor. What is it? E0 divided by K. Okay. And for the electric energy, so we have this form. For electric energy, we only change this constant, and that's the new energy. Okay. I don't know, with the dielectric, 1/2 some epsilon, which is like K times epsilon naught times E squared. All right. So I want to give you an example, but first I want to talk about the microscopic origin of what's going on. Okay. So let me quickly, this is like an optional section from your book, but I think it's a nice material. Let's talk about it for a couple of minutes. So suppose we start with this capacitor, which is like some E, and there's some voltage, so it's equal to voltage divided by some distance. Okay, and there is some charge Q naught on this capacitor, and we know how this thing works. We work with this a lot so far. Now I want to put this dielectric in between the capacitor plates, and I want to ask what happens, right? So what happens is these dielectrics are generally insulating materials. They cannot have charge flow, but these molecules are like microscopic constituents of this dielectric will align due to this external electric field. Okay. So when they align like this, they are going to have their own electric field, right? For example, I can think of this thing as like, okay, these are so close, they kind of cancel each other. These are so close, they kind of cancel each other. And this one so, this one so. But overall, I will end up with some positive surface charge here and some negative surface charge here. And this whole thing is going to have its own electric field, right? And you can think of this electric field cancellation in a figure like this, right? So there's like an external electric field, and the material gave rise to some electric fields. So basically E0, okay, ED, which we showed, is going to be ED is going to be some E0 times K. But where does this come from? It comes from some induced electric field in this thing, right? So there's like external electric field and this induced electric field. There is some sort of cancellation, and I end up with this ED like this. And I can write an expression for this induced electric field. So this should be equal to initial electric field minus the induced electric field. If I do this, I find the amount of induced electric field in this material, which is going to be equal to 1 minus 1 over K times E naught, right? But okay, now I can think of this thing as like a separate parallel plate, right? There's a parallel plate here, there's a parallel plate here, another one and another one. And if I know its electric field, I know its charge, right? Because for a parallel plate, electric field comes with like sigma over epsilon naught, something like that, right? So then I can think of this electric field as some induced charge divided by epsilon naught, right? Then this induced charge is related to, okay, E naught is sigma 0 divided by epsilon naught. Then this induced thing, okay, let's define it nicely. To make things symmetrical, let's define it like this. This is 1 minus 1 over k times sigma divided by epsilon naught. Then sigma induced is going to be equal to 1 minus 1 over k times sigma 0. Or another way of the same thing, the charge induced should be equal to 1 minus 1 over k times sigma induced. Does that make sense? Yes, we are thinking of the dielectric to be insulator. All right, then let's solve an example. Let's see. I think we have plenty of time, so I can solve this example. So this is example 12 from your book. So the electric in this example partially fills the capacitor. So we have to be careful, right? A parallel plate capacitor has plates of area this much and a separation D 2 millimeters. And the capacitor is charged to a potential difference V naught, which is equal to 150 volts. Then the battery is disconnected and the charge Q on the plates won't change. That's what it means. And a dielectric sheet of K is equal to 3.5 of the same area, but thickness L is equal to 1 millimeter, which is half of its thickness, is placed between the plates as shown in this figure. So we would like to determine the initial capacitance of air-filled capacitor and B, the charge on each plate before the dielectric is inserted. C, the charge induced on each face of the dielectric after it is inserted. And D, the electric field in the space between each plate and the dielectric. Now, there's like some space here and we want to find the electric field there. And E, electric field in the dielectric here. And F, potential difference between the plates after the dielectric is added. And G, the capacitance after the dielectric is placed. Okay, there are a lot of things, but we can go one by one. I'll give you a couple of minutes to look at it, and then we can start. The initial capacitance of air-filled capacitor. How do I calculate this? First of all, there's no dielectric, so that should be simple. Exactly, right? Thank you. So C is equal to epsilon naught area divided by distance. So let's put these numbers. 8.85 times 10 to the minus 12 times, so 250 centimeters squared is equal to 250 times 10 to the minus 4 meters squared, which is equal to 2.5 times 10 to minus 2. 2.4 times 10 to minus 2 meters squared. And I should divide this thing with the distance, which is what? 2 millimeter, which is 2 times 10 to minus 3. So this whole thing should give me something in farad. You can work your units out. So let me calculate this. Divided by 2. Okay, so I got something, I messed up. 11.06. This is 11.06 times 10 to the what? Minus 12, minus 14, minus 11. So I can write it like what? something like, so this is farads. Maybe I can do something like that. 110 times 10 to the minus 12, which is going to be picofarad, right? Something like that. And now B, what is B? Let me read it again. The charge on each plate before the dielectric is inserted, okay? So capacitance, by definition, okay, C is equal to Q divided by V. So here I just calculated C, I know V, then I can calculate the Q, then Q is equal to C times V, which is going to be equal to 0.1 times 10 to the minus 10. This is C times 150 volts. So if I multiply, this is going to be 1.65 times 10 to the minus 8 coulomb. C, okay, we got A, we got B. Now C, the charge induced on each face of the dielectric after it is inserted. So maybe I can draw some pictures here to see. Okay, this is one plate. Let's blow it up a little bit so that we can see. This is the other, and we have some dielectric. Okay, this thing is like this. And there's initially Q here, minus Q here. And after it's inserted, I have some Q induced. If you like, this is minus Q induced. This is plus Q induced. How do I find this? C Q induced is equal to, we just obtained a formula, right? Q induced equal to this, right? This guy, 1 minus 1 over K. So this is 1 minus 1 over K times the charge, which we calculated. So we can do this. I found 1.17 times 10 to the minus 8 coulomb. I'm assuming that's correct, so I'll carry on. Okay, see the charge in the zone, the electric field in the space between each plate and the dielectric. All right, how about this question? I want to ask it to you. The electric field, okay. It's asking you the electric field in the space between the dielectric and the face of the capacitor. What is this? What is the electric field here? Maybe I can ask this way. Does the electric field here increase, decrease, or stay the same? It is going to be the same, right? Let's see how this comes out. So of course there is like some, okay, let's first write the contributions coming from these outer plates. Let's call this, okay, maybe I can use blue. This is like E naught, right? And now there is like some charge contribution here, and its electric field, since this is minus, is going to be this way. And there's some other charge contribution here, since this is plus, it's going to be this way. So the electric field contributions coming from the electric charges on the surface of the electric will cancel each other, right? So this is like, if you like E induced, this is E induced, and these guys cancel. So inside, the electric field doesn't change. So E, I don't know what to call, is equal to E0, does not change. And we can calculate this. What is it? Let's calculate this. It's basically initial voltage divided by distance. which is equal to V over D. It's like what? 150 volts divided by the distance is 2 times 10 to minus 3 millimeter. This is going to be like, or 7.5 times 10 to the 4 volts per meter. Okay. And let's look at this next question. E, the electric field in the dielectric. Okay. What about the electric field here? Somewhere here. Maybe I can ask the same question. Does it increase, decrease, or stay the same? Decrease, right? Exactly. Why? Because there's like an external electric field coming from here. There's an electric field of this material itself. They cancel each other like we argued, and it's going to decrease. And its decrease is given by our formula. So we can write it here. ED is equal to E0 divided by K, right? Is this what we found? E induced plus, so we are talking about E induced plus E0, but it's given by E0 divided by K, so it's going to be equal to 2.15 times 10 to the 4 volts per meter. So A, B, C, D, E, F, the potential difference between the plates after the dielectric is added. Okay. So F, potential difference, V, is equal to E dot dl, which is going to be equal to some E0 times, okay, D minus L, okay. So E0 times this distance plus E0 times this distance is the contribution to potential coming from other plates. And inside, it is going to be equal to plus E0 divided by K times L. And I can take everything in the E0 parenthesis, if you like. E0, okay, D minus L plus L over K. Okay, let's calculate this. This is 9.6 times 1, something like 96. Fine. 96 volts. Okay, here what is important is you have to be careful. This is not equal to V0 over K simply, right? If you calculate the V0 over K, so this is like a warning. If you calculate the V0 over A, let's find what it is. It's like 150 divided by 3.5, which is equal to something like 42.8, something like 42 volts. So we didn't get that, okay? And this is because it's the electric is not filled entirely. So that's important. And G, capacitance after the electric is in place. Okay, let's do this and give a 5-minute break. Fg, okay, C is equal to Q divided by V. We calculate both Q and, okay, Q is equal to what? Where is the Q? Q is equal to 1.65 times 10 to minus 8 coulomb, and I divide this thing with the voltage. I calculate 96 volts. 1.7 times 10 to the minus 10, or this is to compare with this, 170 times 10 to the minus 12 farad. So capacitance almost increases like, I don't know, let's calculate 110, okay, maybe the other way, 170 divided by 110, 1.5 times, 1.5 times increase. Okay. Also, you have to be careful, this one also not, and this also not. C is equal to K times C0, which would be like, what would be like 3.5 times. So basically we calculated V from the definition, right? V is equal to E dot dl. And for E, there are like two regions. This region in which E is constant, and this region in which E is constant. But this constant is different from the E here because there is like a induced electric field which cancels somewhat. So I calculated the first part, this and this, and I calculated the second part, which is the middle. And if I add everything up, like I found this 96 volt. And I said this 96 is not simply V0 over K, okay? If the capacitor filled the whole thing, it was going to be simply V0 over K. But since it's not, there is like a little bit difference. And the same thing here, I calculated C from its definition, and I found something like this. And it was not simply K times C0 because the capacitor doesn't fill the entire region. If it fills the entire region, I would get exactly this and this, okay?